Again, say it again.
This is for you, Pop. I'll try and make this short and sweet, or maybe I'll just stay after school for an hour and a half and just
Make it as long as you can.
2 hours.
Pop is an op.
Okay. So here's what we have left between now and kind of Christmas. So we have this unit on like working energy. We won't get done with that until like after Thanksgiving. So we'll get a lot of it done, we won't get the whole thing done. And then after that, when we've got like gas laws, got thermodynamics, like airflow with air pressure and that type of thing. Then we've got like a written final and then a 2-day lab final. So that'll be the last 2 days of the class. So then we go Monday, Tuesday, Wednesday, right before Christmas, I think. So your written final will be on that, if that's right, your written final will be on Monday, and then your lab final will be Tuesday, Wednesday. So, and lab final's kind of fun, it involves razor blades and fire, so that's kind of fun. Yeah. Okay, so, to start this off, we need to talk about this concept of work. Now, work from a physics perspective is similar to your typical definition of work, but yet it's not. So, if you look on your sheet, the equation for work is pretty much as simple as it can possibly get. So on here, you've got, where's that? Maybe it's on that yellow sheet.
Work equals force times distance.
Yeah, it's force times distance, but sometimes they write it in a weird kind of way.
It's like midway through the first paragraph.
I'm looking at that on that purple sheet. Okay, so you got work equals force times distance. That's the short version. So let's talk about the unit. So that is going to be in newtons. That's going to be in meters. So one option with work, you could put newton meters. But the more correct version of this is to put units of joules, which is a measure of J. Now, what you'll see also is that work is also a measure of energy. So if there's one like overarching theme that unifies about every branch of science, biology, chemistry, physics, okay? And that's this concept of energy. So, and that energy is going to be the next big topic after work. So work we're going to basically get through today. On Monday we'll start on energy. So the unit of joules is named after Prescott Joule. And so Prescott was probably a pretty popular kid in high school because his family owned a brewery. And so it's like, okay, hey, party at Prescott's, dude, okay? And so Prescott was the first one that measured quantitatively the relationship between thermal energy and mechanical energy. So what he did was that he took like a sealed container, and within the sealed container he had a rod and it had like some baffles on it. And then he had a rope tied around this that came to the pulley system, and then the pulley system would drop a weight. So as the weight fell, it would make this turn, okay? And so what he was able to do is he was able to measure the temperature changes within that system. Now, this is something that you all intuitively understand. So let me give you this. You have two identical Yeti thermoses, or whichever one you want, the Yeti or the thermos of your choice. Both filled with the exact amount of ice and a little bit of water. One, we're just going to sit here, okay? The other one, we're going to start shaking like this, okay? One's going to sit here, one's going to continuously be shook. Which one's going to melt faster? The one that sits here, the one that's being shaken, or they're going to melt at the same rate?
Shook.
Why?
Because since you're shaking it,
So
giving
what?
off heat.
What's heat?
Friction.
What's friction?
Vibration of
Joules.
particles.
It's particles moving around, right? Same thing is true, it's cold outside. You've lost your mittens. What do? You do work, right? You exert a force over a distance, and that's creating thermal energy. And so the same thing is going to be true of that container. So what he was able to do was basically say, look, as this weight falls, that's potential energy changing into kinetic energy. Then he said, okay, if that's the case, then he was able to quantify, measure very precisely the increase in the temperature of the water. And so he was able to say that this mechanical energy here, as that weight falls, translates into an increase in thermal energy within the system, okay? And that's why units of energy are named for joules. So if the more you study science, the more you'll see this unifying theme of energy is, you get into chemistry. It's like, oh, whoa, what's chemistry? One level chemistry is just, it's the study of energy. It's like, oh, okay, I drop a piece of magnesium and hydrochloric acid. Oh, it gets really hot. Oh, energy is being released. You burn gasoline in your cars. Oh, okay, well, that releases energy, okay? That's why your engine gets hot, because of the fact that combustion process is releasing energy, okay? So if you've ever seen like some of those, like if you get an injury and you want a cold pack, there's some like if you break them or snap them, it gets really, really cold. So sometimes energy is taken in, most reactions energy is given off, and that's a whole lecture on entropy and thermodynamics. So here's the deal with work, okay? So as we go through this, you need two criteria to have work, okay? First off, you have to have a force, and that force has to move through a certain displacement, okay? So let's say, for example, I take this block, okay, and I pull it along like this, okay, and I'm exerting a certain amount of force. So as I pull this block, I just did work, because I exerted a force over the distance. So as simple a calculation as I could possibly do is that, let's say that took me 1.2 newtons of force, and I pulled that thing for a half a meter. So I did 0.6 joules of work, okay? Now, if you want to look at this from a graph standpoint, if you were to draw a graph of force and distance, okay, so this is going to be different than change in momentum. Change in momentum, remember, was a force time graph. This is a force distance graph, but it's the same idea. So if I exert that force over a certain distance, guess what? The area underneath that graph represents work. And obviously, if you think about it, the farther I pull it, what's going to happen to the work that I do?
Increase.
It's going to increase, so that area will get bigger. So the more force that I apply over a greater distance, that gets me a bigger area. I do more work, okay? Now, work can also be a negative value. So work is all about the preposition. So in this situation, if I pull this thing, what we talk about is the work that's done in pulling the block. So if the force is in the direction of motion, okay, if force is in the direction of motion, that's defined as being positive work. Now, here's the deal. And this is the other thing that you see, a whole bunch of random things that we've done start to come back into focus again, but we're just going to repackage them a little bit. So as I was pulling that block, and let's say that that took 1 Newton and that's my force applied, what's the only reason that I have to keep applying that force to begin with?
Friction.
Because there's friction. If there was no friction, would I have to keep applying the force?
No.
No, I could just go doink, and it would move across. So the only reason that that force is there is because of the fact that there's a friction force. So if my applied force is 1 Newton, and I'm at a constant velocity, what's the value of my frictional force?
1 Newton.
Oh, that's gonna be negative 1 Newton, right? So my forced friction then is gonna be negative 1 Newton. Okay, now, so the work that I do in the direction of motion is a positive value. So the work, you gotta get used to the terminology. So the work done in pulling the block is defined as a positive value, because that's going in the direction of motion. So the work done in pulling it would be 0.60 joules. Now, you also can talk about the work done in overcoming friction. So my frictional force is in the opposite direction of motion. So if the force is in the opposite direction of motion, that's defined as negative work. So the work done in overcoming friction would be a negative 1 Newton times 0.5 meters, which would get me negative 0.6 joules. So work can be positive or negative depending upon the situation. Now, that negative 0.6 joules exists pretty much as like a bookkeeping function. So here's what I want you to see, is that when you rub your hands together, do you feel warmth? Yeah, okay. If you've ever seen the survival shows and they need to start a fire, what do?
They rub the sticks.
Oh, they rub
Yeah,
sticks.
they rub sticks.
Are they doing work?
Yes, they're working.
Yes, okay. So have you ever seen them, they'll take like a hollowed out piece of wood, okay? And they'll put that rod in there. And some of them get real fancy, they have ropes that'll go back and forth, some of them just use your hands, right? But here's the deal. If you don't do any work, guess what? You're not gonna start a fire, okay? It's the reality of it. You're not gonna start a fire. But you have to do a lot of work depending upon the situation. So you might have to rub that really, really fast and really, really hard to generate enough thermal energy to start that fire. So here's the point. When I pull this thing, okay, there's some friction that I'm overcoming, and that's generating a little bit of heat. Now, I don't have to worry about dragging this thing. Oh man, my paper's caught on fire, okay? It's like, oh, I'm cold. Let me push this. Oh, that feels much warmer, okay? No, it's not a tremendous amount of thermal energy, but there's some, okay? If you've ever, is anybody ever like pulled a nail out of a piece of wood or something? Okay? It feels hot, okay? Or if you've taken a screw out of a piece of wood and you take that out, that friction has made it feel hot. So friction is a form of energy because you're doing work in the opposite direction of motion. Okay. Now, here's the deal. So we have force applied and we have force friction. What else is there working on the block?
Force of gravity.
Gravity and
Normal.
normal. Now, here's the deal. When I calculate work, I don't care about those because I only worry about force that's in the direction of motion, okay? So, yeah, gravity is pulling it down. I don't care. It's not in the direction of motion. The table is providing an upward force. Don't care. Not in the direction of motion, okay? Now, here's an interesting idea. So I take this block and I just hold it like this, okay? Am I doing work?
No.
Why not? I'm exerting a force, my arms can't.
It's not moving.
Yeah, it's not moving in the direction of
Motion.
motion. Now, what if I take this block and I lift it up?
Yes.
Now I do work. Why?
Because it moved in the direction of motion.
Now, so the work that I would do would be defined as a positive value because I'm lifting it in that direction, okay? But the work done in overcoming gravity would be defined as negative value because that's in the opposite direction of motion. Now, if I lower it back down, okay, then the work done in overcoming gravity, right, because gravity is pulling this way and that's going in that direction. That gravitational work would then be actually, if I let go of it, oh, gravity is pulling down this way. But if I lower it, if you think about it, my upward force is in the opposite direction of motion. So if I lower it, I do negative work, gravity does positive work. But if I lift it up, I do positive work, gravity does negative work. Okay. Now, what would happen, let's just say,
We shot Louis.
I take a rubber stopper,
I can't.
and once I get it up to speed, okay, once I get it up to speed, am I doing any work? Why not, Jackson?
Because you're not exerting a force.
Yes, I am.
And it's not.
I'm completely exerting a force, because if I don't exert a force,
No, you're not, because there's only two forces acting upon it, and it's not in the direction of motion.
so what are the forces acting on it?
Centripetal, which is pointing perpendicular,
Okay?
and then gravity, which is pointing down.
So if you look at that rubber stopper, okay, I was exerting a centripetal force, which is inward at a
90 degrees.
90 degrees.
to the velocity vector. So I'm exerting a force. But is it moving? Is there displacement in the direction of that force? So I don't do any work. Okay? I'm exerting a force, but again, I'm not doing any work. Here's the Earth. Here's Joe's satellite orbiting around the Earth. Work being done on satellite?
No.
Why not? Same idea,
Centripetal.
right? The centripetal force is acting
Inward.
inward, but it's not moving in that direction. Now, if the satellite orbit begins to decay and it gets closer and closer to the Earth,
Yes.
then it will do work. Okay? Got that?
Got.
Got it? Now, what if I pull this block at an angle like this? Okay? So visualize this.
Yes.
Am I doing work?
Yes.
Yes.
But what's the only force that I would consider?
Force.
The tension,
No.
the vertical component.
A horizontal.
The horizontal.
Why only the horizontal?
'Cause that's the
component?
direction of motion.
That's the only force going in the direction of motion. Okay? Now, let's look at another scenario. Hope my voice holds out. I'm fading fast. So let's say here's the bed of a pickup.
It's fading.
Not my best work, but.
It's a thing.
And let's say that the bed of the
It's an M.
truck is 1 meter high. And you have a refrigerator that has a mass of 10 kilograms.
What?
And you need to get it into the bed of the truck. Okay? So you grab it, send it up there. Do you do work?
Yes.
Why?
Because you're applying a force.
You're applying a force over distance. How much work do you do?
Let's see.
Depends which direction.
I'm lifting it up to the bed of that truck that's 1 meter high and it has a mass of 10 kilograms.
More than 98 joules. You have to apply more than 98 joules.
Don't make this complicated.
It's
The
So here's the
10.
deal.
Not
What does the refrigerator weigh?
10
10
kilos.
kilos.
Correct.
98.
It has a mass of 10 kilograms.
98
But it
newtons.
Oh,
weighs
98.
98
Newtons.
newtons, right?
Yeah.
So the downward force acting on this thing,
90.
It's
98
new.
newtons. So if I'm going to lift it up, we're just assuming that I'm exerting just enough force to overcome that.
Yeah, more than 98.
So 98.
Yeah, but I'm just, hold it just a second.
Sorry.
Okay? So in the work calculation, I have to overcome, we just use the 98 newtons as the force value. Because that's what has to be overcome is that 98 newtons. Okay? Otherwise, it's like, well, how much does it accelerate? You just use the 98 newtons. Okay? So I'm going to take 98 newtons times 1 meter, and I would get
98.
98 joules.
98 joules. Okay, that's kind of cool, right?
Yeah.
Now, they're going, that's a lot of work. That's a lot of force. But I happen to have the magic frictionless ramp. Magic frictionless ramp. Okay, now obviously I can't walk up and push it because it's frictionless. But let's say that I could stand up here in the bed of the truck, hook it up to a rope, and pull it. So here's the question. When I do that, am I doing more work, less work, or the same work?
Same.
More. Well, you said it was frictionless.
It's frictionless.
Same. Or
Well,
no,
No,
less.
It's less.
It's
Or
less.
Because you don't have to overcome.
Because yeah, you don't have to overcome anything in it, or else it would be the same if there was friction. 'Cause It's
Okay.
a greater distance.
Well, you have to overcome parallel. But
So
that's
let's say
less.
this is a 30-degree angle, which makes the length of this ramp
so it's more.
2 meters.
38 times 30, so it's like 44-ish newtons.
Okay, so leave everything out of this. Here's a 30-degree angle. Is the downward force still 98 newtons?
Yes.
Yes.
So how am I going to find my force parallel?
G sine theta.
G sine theta.
Force parallel is Fg sine theta.
Yeah.
So if I take 98 newtons times the sine of 30 degrees, I get
49 newtons.
49 newtons. Okay? So that's the force that I have to apply to pull it up, right? So am I going to apply less force?
No.
No.
Yeah, I am.
Well, you are.
Yes,
but-
compared to lifting it,
Yeah.
I'm only going to apply half the
Less
force.
force, but it's the same work.
But what's the trade-off?
It's the same work because it's more distance.
Ah, same work,
Double the distance.
double the distance. So everyone goes, oh, it's going to be easier to use a ramp. It's true. By easier, you mean less force. But what's your trade-off?
You use less force for more time.
No, time has nothing to do with this.
Over
Not
a
throw time into
greater
this.
distance.
Do not throw time into this.
Greater distance.
Greater distance. So basically, it's the same idea, though. In terms of changing momentum, remember it was force times time? Small force, long time, or big force, short time? Same thing, is the same thought process is going to happen here. So what I'm doing is that if you look at a force distance graph, so I can either exert a 98 Newton force over a distance of 1 meter, or I can exert a 49 Newton force over a distance of,
2 meters.
what do you notice about the area?
Equal.
They're the same. So I'm gonna do the same amount of work. What am I trading off?
Distance and force.
Distance for force, which is how all mechanical advantage systems work. You're willing to sacrifice a small force over a
Large distance.
greater distance, which is how mechanical jack works. Inclined planes, they all work off the same, like pulley systems. You're willing to sacrifice force for distance, okay? Now, in reality, there's no such thing as the magic frictionless inclined plane. So in reality, what's gonna happen to that force?
Going to.
It's actually gonna be
Larger.
bigger, because you have to overcome friction.
Right.
So in reality, you're actually gonna do
More work.
more work, because you're gonna exert more force than the 49
Over a greater distance.
over the 2 meters. But even if it's, here's the argument, even if it's 60 newtons, well, 60 newtons is still less than the 98 newtons it would take to just lift it up there, okay? Stop that for a second, I need to get something to drink. As quickly as I can.
No, like rubber stop.
Now, here's the next big thing that we need, and that is power. Okay? So there's a whole bunch of different ways you can calculate power. One version is that it's work done divided by time. So if you look at work, work's gonna be measured in what? Joules. Time's gonna be measured in,
Seconds.
so it's joules per second. Okay, so that's one option of how you can express power.
That's cool.
The other one that you can use is watts. So where have you seen watts?
Light bulbs.
Light bulbs.
I
So what's
know.
brighter, a 60-watt bulb or a 100-watt bulb?
100 watt.
100.
Why?
They're more powerful.
There's more energy per
Second.
unit of time. Okay? So let's say that I want to lift this 1 kilogram mass to a height of 1 meter. So I got a 1 kilogram mass that I'm going to lift up to a height of 1 meter, right? So how much work am I going to do? Jackson?
1. Wait. Hold on. Yes.
Yeah.
No.
9.8.
joules,
9.8 joules, why?
because it weighs 9.8 newtons. And you make-
Yeah, it's force times distance, it isn't mass times distance, right?
Yeah.
So the work that I'm gonna do is 9.8 joules, because 9.8 times 1, check my math, is 9.8. So that's the work that I'm gonna do. Now, if I do this, and I lift it up, and I time it, and let's say that takes me 1 second. Oh, okay. So, to calculate the power, that would be 9.8 joules. This is a rate function. So it's 9.8 joules per 1 second, which would give me 9.8 watts. Okay? Got that?
Yeah.
Now, Louis goes, "Fuck him, you're old." I said, "Yeah, so what?" So I said, "Louis, come up here." So Louis comes up here and he goes, "Whoo, look at me," right? So instead of taking 1 second, Louis does it in a half a second. So who's going to do more work, me or Louis?
Same amount of
Same
work.
amount of
Same amount of work, right?
Just more watts because it was less time.
Oh, so Louis does the same work in
Less time.
that requires more
Power.
power. Okay?
Power.
Now, the other way, and we'll talk more about this on Monday. But work also, as a general rule, equals a change in energy. Okay? And we're going to spend a lot of time talking about energy. We're going to talk about gravitational potential energy. We're going to talk about kinetic energy in a spring, or kinetic energy, linear. We're going to talk about rotational. We're going to talk about OOE, which is electrical potential energy. So we're going to talk about UG, which is gravitational, OOE, which is electrical. Linear kinetic energy, rotational kinetic energy, energy in a spring. We're going to spend a lot of time talking about energy. And guess what units they're all measured in?
Joules.
Joules. Okay?
Good try.
What'd she say?
I said watts.
Said Newton meters.
JJ watts.
No,
Okay.
that's power.
So, one way to look at work is a general rule. Work is equal to the change in the energy. Okay? It's a generic way to look at it, is change in energy. So, power then is the rate at which your energy changes. Okay? So it's a change in energy per unit of time. And if you think about it, you're driving your car, right?
Yeah.
And you can go from 0 to 60 in 1 minute. Okay?
That's Pop's car.
Corolla.
That's
Or you can
Pop's
go from
car.
0 to 60 in 6 seconds.
My car.
What's going to require more power?
Vito's car.
Less time. Why?
Second one. There's less time and the same amount of work.
Yeah, it's a greater change.
Changing.
It's a rate function. You're changing your energy at a higher rate of change. Okay. So you got that idea.
Sure.
Now, you can also get a little bit fancy with this. You can go power is work divided by time. But power is force times distance divided by time, right? So what can you do with distance divided by time?
Velocity.
Velocity.
Ooh.
Oh, so you can also write it as force times
Velocity.
velocity. Now that makes sense, okay, if you think about it. So here's your car. And especially if you ever own an electric vehicle, which I'm guessing in your lifetime most of you will, batteries only hold so much power. So you need to be aware of this equation, because that's force times velocity. So the faster you drive your car, what's going to happen to the power requirements to do that? It's going to go up, okay? Now, force will be a huge factor. Let's say that you're driving your car down to Oklahoma City and you're fighting a really, really strong south wind. That resistance force is going to go up. So what's going to happen to your battery life?
Down because your acquired force goes up.
Yes, because that force is going to go way up. Now, if you're driving down there today where you have a strong north wind, it's gravy, right? Because the power requirement is not going to be as much because you won't have as much force because the wind is blowing with you. So if you ever drive a battery-powered car, remember this equation, that power is force times velocity, okay? Just remember that. Okay, stop that for a second. I gotta go set up a quick demo,
Outro.
and then we'll go to the back. Stop these.
Hold it.
Yep. Okay,
It's blocking the visual.
so here's what we've got. Are you recording?
Yes.
Mine away.
You're okay.
No, you're good now.
Yeah.
Okay, so here's what we've got. So we've got the same force, 50 grams, okay, 0.49 newtons, suspended from the end of each string, right? So when I let go of it, just don't let go of yours, right? When I let go of it, it begins to accelerate, right? So is work being done on the cart?
Yes.
Why?
Because there's a force being applied over a distance.
Okay, there's a force applied over distance, right?
Yeah.
Now, let me let go of yours. Now, is work being done on Louis' car?
Yes.
Yes, right? Now, here's what I want to look at. So the first situation, I'm going to let go of it, but we're going to let it go for the same time, okay? So what I'm going to do is we're going to let it go, and then I'm going to tell you to stop it when yours gets to about here. Okay, right? So I'm going to let go, I'm going to go 1,001 and probably stop it. Ready? Okay. So, ready, set, go, 1,001, stop it.
No, you're supposed to stop it.
to stop it, bro.
No, that's what I was telling you.
Gosh, Louis.
Okay, all right.
I'll stand to this side.
Pop.
We're good.
Top head don't need to see it.
Okay, so you ready? Gonna go 3, 2, 1, go. Stop it. Now, which one underwent the greater change in the momentum? Louis' cart or my cart?
My cart,
Why?
because it has more mass and it went kind of the same distance.
No. How
Your
do you
cart.
calculate change in momentum?
Your car was going faster.
No. How do you count?
Mass times velocity.
Last time velocity.
Or,
And
what is else change in momentum equal?
Force times time.
Force times time.
force times time.
Was it the same force?
Yeah.
Yes.
Same time.
Same time,
Yes.
Equal.
Equal.
same change in momentum. Okay?
Cool.
So they both underwent the same change in momentum because of the fact that same force acted over the.
Same time.
Now, which one ended up going faster?
Yours,
Why?
last round.
Yeah. So for this to have the same momentum as Louis', so Louis had more mass, his had to be going
Slower.
to have the same momentum as.
Smaller cart.
Now, which one had more work done on it? Louis' or mine?
Yours. Yours went farther.
Mine went farther. Same force,
Yes.
Oh, yes.
greater distance.
Correct.
Yeah, so yours.
So mine had more
Work.
done on it because we kept the time the same, but the distances weren't. Which one accelerates faster?
Yours.
Why?
Less mass.
Same force,
Same force.
same force, less mass, greater acceleration. Now, pull that back up. Now we're going to let them go the same distance. Okay, so we're going to go from here to about right here. Okay, Ready?
What are you at? Like 43?
Yeah, about 43. Okay, ready? 3, 2, 1, go. Now, which one underwent the greater change in momentum? Mine or Louis?
Equal
Mine.
change in moment.
Why?
Because it was longer time.
Force times time equals change in momentum. His force acted over a
Greater time.
Greater
great amount of
time.
time, so his car, even though it took longer, actually underwent a greater change in momentum. Now, which one had more work done on it?
They were the same.
Equal work.
Why?
They went the same distance.
They went the same distance. So in this situation, they were the same work because it was the same force acting over the same distance. Okay? Force times distance equals work. Force times time equals
Change in
change in momentum. Okay? So that's what you want to keep straight. In both situations, it's the same force. So we're either going to keep time the same or we're going to keep distance the same. Got that?
Yep.
Yes.
Okay, back we go.
Say what's up to the vlog, Luke.
Skinny penis.
I still think it's funny.
I know,
think it's funny.
I don't. Anyway.
Run it back.
Okay, so let's talk about question number 8. So we're also going to introduce density into this.
Oh, yep. That's fun.
So here's this crane,
That's a good crane.
and it's lifting up a bucket.
What?
You should be an artist.
No, this is just years of being bored in physics lectures. Okay, you get pretty good at doing. All right. So the bucket, oddly enough, needs to lift something because cranes that just lift empty buckets don't sell very well. What does your crane do? It lifts empty buckets. Is that it? Yeah. It looks cool.
Ukraine
Does it do
fights
anything?
Russia.
No, it just lifts empty buckets.
Ukraine.
Not probably going to sell very well. So here's the deal. So what you who have studied chemistry have probably seen density written as density is mass divided by volume, and the units were probably grams per cubic centimeter. Because in the chemistry world, they work off of the GCS system. They work off of grams, centimeters, seconds. Okay? Physicists work off the MKS system, which is mass, kilograms, seconds. Okay?
Wait, mass?
Or excuse me, meters, kilograms,
Okay.
seconds. Meters, kilograms, seconds. So, and the formula even is different in
After that last test, use the KMS.
so
You joking?
the units are, the formula is even different. So in physics, we'd write it as rho equals mass divided by volume. So this is the Greek letter rho, which kind of like, looks like a jacked up P, okay?
Yeah, I've seen it
Right.
on the sheet.
Huh?
I saw it on the sheet at the place yesterday. I was like, oh, that's a fun letter.
Yeah, so this is the Greek letter rho. So, but it's the same idea. But the difference is that the mass here is gonna be in kilograms, and the volume is gonna be in cubic meters. So like in the density of water in a chemistry class is 1 gram per cubic centimeter, because they deal with smaller quantities. Density of water in the physics class is 1,000 kilograms per cubic meter. Okay, same ratio, but imagine instead of having in chemistry, a cubic centimeter is about the end of your pinky. Okay, 1 gram is about the same as a paperclip. In physics, you have a cubic meter, okay, which would be 1,000 kilograms. Okay, so the same ratio, just different numbers. So here's what's happening on number 8. So I've given you the bucket by itself. The bucket just by itself is 2.25 times 10 to the third newtons. It contains within the bucket 1.15 cubic meters of soil. So there's your volume. I've given you the density of the soil, 2,000 kilograms per cubic meter, so that's about twice the density of water, okay, which means this stuff would sink in water.
Cool.
And you want to calculate the work that's done. So the first thing that you need to do is realize that you're lifting two things. you're lifting the bucket, and you're lifting the dirt, okay? So you need to find the weight of the dirt. To find the weight of the dirt, you need to find the mass of the dirt, but you know the density and you know the volume. So what you need to do is take the density of the dirt times the volume of the dirt to get the mass of the dirt. Multiply that by G, there's the weight of the dirt, add that to the weight of the bucket, boom, you're off to the races. Okay. When you get to number 11 is going to play out just like I just did back there.
Okay.
So you have two objects of unequal mass, A and B. Mine's Louis', okay? We're going to have the same amount of force. We're going to put the same weight on the ends of the string, okay? Mass A is larger than mass B, okay? And the time is going to be the same. So both of these are going to move for 2 seconds, okay? Time is going to be the same. One's more massive, one's less massive. So I ask you, which one will travel further? Explain. Now, in big bold letters at the bottom of this question, I tell you, as part of each answer, you should include an equation to justify your answer. So what you cannot say is that, let me see, I think it's going to be mass B. Why? Well, it has a greater acceleration. Okay, so what does it mean? How does a greater acceleration translate into a higher velocity or a lower velocity or more work or a greater change in momentum? Okay, so I'm not saying you can't use acceleration, but you cannot just saying, oh, it has a bigger acceleration or it has a smaller acceleration. That doesn't justify, oh, it has more work done or it has less work done. So you need to justify it in terms of like a kinematic equation, or the idea that change in momentum is equal to force times time, or work equals force times distance, okay? So you just can't say, well, it has a smaller acceleration. That won't cut it. And then you've got some questions out and problems out of the book.
Yes, sir.
Okay, my voice was dying. Call it good.
Coolest
Let's get the
outro.
test.
Might get the coolest
You know
outro.
why I don't teach freshmen?
Is it 13?
Or 'cause